Hi, I'm Simon Devitt. I'm the scientific lead on the meQuanics project and currently a senior research scientist at the Japanese Institute RIKEN. Over the past 10 years, myself and colleagues have been responsible for the design of many large-scale quantum computing and communications architectures. Ever since the first proposals for quantum computing were put forth in the 1980s and 1990s, researchers from around the world have been in a race in order to build a new class of exciting new technologies based upon the often spooky and weird rules of physics at the atomic scale. Quantum technologies has the potential to revolutionize the information sector in the 21st century because of the ability for quantum computers to perform calculations in a fundamentally different and faster way than a standard computer. The success has already been quite significant, with newspaper article after newspaper article being released showing that quantum engineers can now successfully fabricate and control very small quantum computers consisting of only a handful of quantum bits, or qubits for short.
Experimental physicists and engineers at both universities and private corporations have demonstrated small quantum computers in a variety of physical systems. Notable examples include researchers at Google who have recently demonstrated a highly accurate quantum computer in superconducting circuits, research that was mirrored at IBM. Physicists at the University of Innsbruck in Austria can create small quantum computers using cooled atoms. Australian researchers in 2015 demonstrated silicon-based quantum technologies, and a large effort at the University of Bristol has pioneered qubit technology using single particles of light known as photons.
Although still in its infancy, physicists and engineers have proven that quantum technology can work, and with continued investment can hopefully revolutionize the sector. However, there is still much work to be done.
Although quantum computing systems can be physically very different, the general operating principle for all architectures are identical. The hardware prepares a regular lattice of qubits, which are then sequentially measured as computation proceeds. The way in which these qubits are measured allow us to define the geometric structure and execute a quantum circuit. These circuits are topological in nature, which allows us to do something interesting.
If you stretch and mold the shape of a coffee cup without breaking it or cutting it, you can turn it into a donut. The structures are topologically equivalent. They have a single hole. In this way, topological quantum circuits have the same properties.
In this model of quantum computing, the quantum circuit itself is actually a complicated three-dimensional puzzle, with pieces of the puzzle winding around each other like a ball of string. It's this weaving and braiding that actually performs the computation, and its physical size tells us how many qubits and how much time we require in order to perform the computation. The aim of meQuanics is quite simple. We provide the player with a quantum circuit. This circuit is then encoded using the complicated techniques and theorems into a three-dimensional puzzle. The player's aim is then simply to make this puzzle smaller. That's it. meQuanics folds in all of the complicated quantum physics and quantum information into its code base, such that the player cannot actually change the algorithm being implemented. But by making it smaller and smaller, they reduce resources and allow you to actually program a future quantum computer. At this stage, due to the infancy of some of these techniques, we don't actually know what the best techniques are in order to optimize quantum circuits for real-world hardware. We don't actually know if it's possible to find optimal solutions, and we still don't know if we've found all the rules for circuit manipulation that quantum physics allows for. meQuanics is a first attempt to generate usable data that can be directly applied to future quantum hardware or serve as a valuable starting point for the next generation of complex algorithms that will help us solve this optimization problem.
meQuanX is the first crowdsourced project in quantum computing that is designed specifically to solve an important scientific problem. meQuanX is an attempt to use the creativity of the human mind to produce solutions that will be directly implemented on future quantum computers.